Okay, so I wanted to record a little video which covers the topic of synapses. Now, you do not have a question which explicitly asks you about synapses, and it's not part of the criteria, but it's kind of useful to have at least rough understanding of how synapses work, because you can actually kind of link some of this information to the practical, which is the last question. So that's why I kind of wanted to mention at least synapses and briefly summarize how they work. So if we consider a neuron, so you should be able to recognize a picture like that. So you obviously have your dendrite, then you've got your axon, and as we discussed before, the impulses always go from the direction from a dendrite towards the axon and towards the end of the axon, which is called axon terminal. So at some point, this impulse is going to keep on traveling from the dendrite onto the axon and carry on until it gets to that bit. And this is where the impulse will need to get from the end of this neuron to the beginning of the next neuron. So it's going to be going from the end of the axon to the beginning of the dendrite of the next neuron. And here, what we have is a tiny gap. It's not a big gap, but it's still a gap. And the same is going to be happening at the other end, right? So in order for that neuron to receive a message, somehow it had to get that message from the end of the previous neuron, from the end of that axon. So what's going on then in that section, in that gap? And what you have to remember is that the nervous impulse, it's electric in nature. So it's a bit of tiny bit, it's a bit like a little bit of electricity which is running through a wire. And you can imagine if you have a cut in the wire, if there is a gap, then that electricity would struggle to get across, right? So if you cut through a wire, say, in your, lamp, say, table lamp, then the lamp will stop working because electricity is not getting to the bulb. So how does nature solve that issue? What is going on in this gap? So that gap and that kind of way of connecting the two neurons is called a synapse, right? So here is my kind of next diagram to show you the structure of a synapse. So I'm going to cover part of it for now, and then I'm going to add another diagram. So here is the axon terminal. So that's the end of the axon of one of the neurons, and that's the beginning of the next neuron, the dendrite of that next neuron. And here is my little gap. So that gap is called synaptic cleft. Synaptic cleft. And what you have in the axon terminal are little sacs which are filled with specific molecules called neurotransmitters. So these sacs are also called vesicles, by the way. So they're vesicles filled with molecules of neurotransmitter. And I've drawn each molecule of neurotransmitter as a red dot inside those sacs or vesicles. And on the dendrite, right at this end, you have your sodium-ion channel. So this is something we came across before in the previous video where I covered nervous impulses, right? And in order for the action potential to occur, the sodium-ion channels need to open. So we somehow need to get those sodium ion channels to open. So how does that work, right? So what happens? So when you've got action potential coming in to the axon, it is acting on that axon. And what actually happens is you have other type of channel here in the axon terminal. I didn't draw them here because I just didn't want to overcomplicate and have too many labels, but I've drawn them on this picture. So in this green, I've got special channels, protein channels, and they are specific to the ions of calcium. So ions of calcium can get through these channels, and so when action potential or nervous impulse arrives to the axon, that triggers those calcium ion channels to open. So I'm going to draw a whole bunch of calcium ions. So calcium ion is capital C, little a, 2 plus. Okay, so that's calcium, Ca. 2 plus shows it's a charged particle, it's an ion. Okay, so let me draw a few more. So those calcium ions then enter and they start pushing on the vesicle. So you see that they were here, sort of suspended all over the axon terminal. But when calcium ion gets in, calcium ions start to push on these vesicles, and the vesicles start to get closer and closer to the membrane, to the point where some of them just burst through, a bit like bubbles, rising to the top of a champagne glass and just bursting through, and whatever the content of those bubbles, it's just going to come out. So it's a bit like that. So the neurotransmitter, which was initially trapped inside those bubbles, inside those vesicles, that neurotransmitter is starting to come out into the gap, into the synaptic cleft. And as it's coming out, it's starting to also drift across towards dendrite, because that's just simple diffusion, isn't it, here? So you've got a bunch of these neurotransmitters to start with at this end, very little at the dendrite end, so it's just going to start slowly drift across, a bit like perfume, drifting across from one end of the room to the other end of the room. And when neurotransmitter gets to this end, what it actually does, it opens those sodium ion channels. So neurotransmitter causes the sodium ion channels to open. So they open. And as soon as they open, then sodium ion gets in, and we talked about it before. So as soon as sodium is able to get in, then that means that that's beginning of nervous impulse or action potential. And so therefore, that's going to now generate the action potential or on the dendrite and or on the next neuron. So action potential. Now, you don't actually need to explain all of this in detail in your assignment at all, because, as I said, it's not explicitly in the criteria. But what is useful to know is that synapses have several qualities, and one of these qualities is called temporal summation. And again, let me start by sort of closing part of this diagram to begin with. So what temporal summation says is if you have low frequency of impulses coming to the axon, to this axon terminal, that causes very little amount of neurotransmitter to get released into the gap, into synaptic cleft. So you have low amount of neurotransmitter. And that means, in turn, that actually you're not opening enough sodium channels to generate impulse in the next neuron. So actually there's no impulse which is created. So what do I mean by low frequency? Well, if you watched my video about the graph for nervous impulse, you know that it's got that shape, and it means that there is a big gap between one impulse onto the next and onto the next, right? So that's what low frequency means. So it may be because there is some kind of very little irritation going on, right? So maybe it's again some clothing rubbing against your skin and you're not even aware of it, or it might be some noise coming from the road and you live next to it for so many years you don't sort of notice it. So there is still kind of action potential which are being generated in the first neuron, the one which is maybe closest to your ear or your eye, where it's still picking up the signals. But because they're low in frequency, it never gets passed onto the next neuron, and so therefore it never reaches your brain, and so you're not aware that there is some kind of a little bit of irritation going on in the environment. Now, if you have, however, situation where you have high frequency of signal. So let's have a look at this picture. So it means those peaks are really bunched close together. That causes a lot more neurotransmitter to get released into this gap, and that means that you're opening enough sodium channels to pass on that impulse onto the next neurons. So that means that ultimately it'll probably reach your brain, and you're going to be aware that there is something going on and going to maybe react to it. So that's what temporal summation is. So why is it important? Why am I talking about temporal summation? Because when it comes to your last question in the assignment, you're going to do this practical where you're going to record your reaction times. And you're going to record these reaction times in a couple of different conditions. So it could be maybe, I don't know, normal lighting versus low-level lighting. And this is something which can help you to explain and link your results to the physiology. So why is it that, you might be have lower, say, reaction time when in low lighting? Well, you can sort of link it to the fact that actually, because you have low-level lighting, so you probably have low frequency of impulses. So less light reaches your eye, and therefore less amount of impulses are being created, and so therefore your brain is struggling to process information because it doesn't reach the brain quite in the same way as you have kind of bright light and a lot of impulses are reaching your brain, right? Because if you have lots of neurotransmitters, high frequency of signals. So this is how you can potentially link results of your practical to the physiology. Right. Another way you can link them is by talking about also the threshold potential, which I talked about in the previous video. Okay, so that's it really for the synapses. As I said, don't get too worried about it because it's not, as I said, explicitly part of the criteria, but if you wanted to make your kind of analysis of the practical results richer and more interesting and a bit deeper, then this is the kind of thing you can potentially talk about. All right, thank you very much, and that's it for now.